Good morning, friends. We are again back, and last class we decided that we will now develop perturbed equations of motion. When I say perturbed, it will implicitly mean that we are talking about small perturbations. And to show you an example, I have picked one equation that is along body fixed x direction, which is this. XYZ body fixed, and u is the component of total velocity resolved along x. And u, this is v, this is w. And we are writing equations along x, y, and z axis of one equation. We have demonstrated here, and we are presenting here, that is the acceleration along x direction, represented by this equation. Well, you very well know these are the external impetus force, because of gravity, because of dynamics, because of thrust and propulsion. We are looking for how to develop a perturbed equation of motion, and our understanding was that total u, once the perturbation of small u is reduced, this perturbation is small, so we can use the linearity. You also understand when I talk about small perturbations, the product of the perturbed quantity is negligible. Right? You said, okay, we are introducing this perturbation about a steady state. Physically, it means if I am flying level cruise, which is our steady state in this case, and let's say I just given a elevator deflection and withdraw, the velocity will change, the angle of attack may change. All those things, we are representing the change of the perturbed quantity represented by small u, small v, small w, like that. We say total v will be v at steady state plus small v, w will be w at steady state plus small w. Similarly, p plus small p through pitch rate q1 at steady state, the small q, yaw rate r at steady state, the small r. Similarly, to extend the small perturbation understanding, we will say theta at any time is theta at steady state plus perturbed theta, psi at any time is psi at steady state plus perturbed psi, and phi is phi at steady state small phi. Now what we will do, we will use this and we will substitute this in this equation. Okay? Let's see what happens. So what will happen? It's a mechanical approach. You see, I write m for u. What should I write now? u1 plus small u. Okay? It will be u1 plus small u dot, then minus v1 plus small v r1 plus small r plus w1 plus small w and q1 plus small q. This, I now erase this part. You know this will be equal to minus mg sine of theta 1 plus small theta plus f ax1 plus fax plus f px1 plus f px. What are these fax and fpx? They are the perturbed aerodynamic and propulsive force. The question comes, how this perturbed aerodynamic force will come? You understand, if I am flying at a cruise and suddenly I have given some disturbance, so its angle of attack may change. The angular attack will cause change in the lift, the drag, so the aerodynamic forces will change. Similarly for propulsion side, if it is a, let's say, propeller driven engine, as there is change in angle of attack, there will be change in the thrust in terms of the direction. Right? For example, if I see this is the propeller and suddenly there is a change in angle of attack alpha, you could expect a normal force will come, be generated in the propeller, which will have effect in force as well as in moment. So these are all perturbed. Okay, these are in addition to whatever it was experiencing at steady state. Whatever it was experiencing at steady state is ftx1. And this is because of perturbation, because of change in alpha, change in theta, all those things will look into it. Maybe change in the speed also. Right? We need to understand what are the physical meaning of this. After this, it is just a mechanical thing. And you also should understand that at steady state, this is also identically true. K1 dot minus V1 R1 plus W1 Q1 equal to mg sine theta 1 plus f ax1 plus f dx1. This equation. At steady state, W1 Q1 dot minus V1 R1 plus W1 Q1 is equal to mg minus mg sin theta 1 plus fax1 plus ftx1. Now use this equation as well as use this trigonometric relationship theta 1 plus theta, which is equal to sin theta 1 cos theta plus cos theta 1 sin theta, sin A plus B identity. And we are talking about small perturbation. Let us see here. Which one is the perturbed quantity here? Is theta 1 the perturbed quantity? No. Theta 1 is the steady state quantity. This theta is the perturbed quantity. And our assumption is theta is small because we are talking about small perturbation. Theta is small. That comes from the fact that we are talking about small perturbation. Once I use this information, I can easily write it as is equal to sin theta 1 plus cos theta 1 theta. Because I am using, if theta is small, sin theta is equal to theta and cos theta is 1. Okay, approximately like that. So, better way of writing this is sin theta 1 theta cos theta 1. This is simplification of this expression. If these things are clear to us, and we will be using this expansion of this to find a neater, more meaningful information. So what do I do? Look here, at steady state, this is you understood. So now see this equation. Here, if I write M, it will have U1 dot plus U dot minus V1 R1 minus V1 R minus V R1 minus VR, right? I'm just multiplying V1 R1, V1 R, VR1 minus VR. So here I get W1, Q1 plus W1, Q plus WQ1 plus WQ is equal to minus mg, right? For sin theta 1 plus theta, we are going to write as sin theta 1 plus theta cos theta 1, and then term remains FAX1 plus FAX plus FPX1 FPX. Just mechanical, okay? Nothing extraordinary we are doing. Now see here, if I see this mu1 dot minus v1 r1 minus w1 q1 is identically equal to minus mg sin theta 1 fx ax1 fpx. So I can take out this one. So I will be left with mu dot minus v1 r minus vr1 minus vr. So these things are gone. Then plus w1 q plus wq1 plus wq. This will be equal to mg sin theta 1 will get cancelled. We will have minus mg theta cos theta 1 plus fax1 plus fax1 is also go. We will have ax on the fax plus fpx. Here I am using this. Left hand side I am using this equation, so all this will get cancelled. Also, I take a case where I write that at steady state, what was our steady state? Level 2 is like this. So what is the value of R1? Were there any yaw rate? Was there any yaw rate? No. Was there any pitch rate? No. So was there any value of R1? No. Was there any value of Q1? No. Because it's going like this. Cruise. That is our steady state. So at steady state I can write V1 equal to 0 because I am flying like this, no side compared to velocity. Similarly, I am writing Q1 equal to 0 and somewhere I put R1 equal to 0. If I now put this condition in this equation, what do I get? I get something right at the top. I will get from here equation as m u dot v1 is 0, this goes, r1 is 0, this goes, v into r is the product of two small quantities. We are talking about small perturbation, so this man also vanishes. Here I have left with plus w1 q, and then q1 is 0, this also goes, and wq product of two perturbed quantities, that also vanishes. So this is equal to, remaining is minus mg theta cos theta 1 plus fax plus fpx. This is such a wonderful simplified equation. You can erase this unnecessary, it's taking a lot of space, not giving much of information now, but to understand what we are doing. You see that if I include the small perturbation, then the equation along x direction, what is the x direction, gets simplified to this, but you should not forget what are these u theta and q, these are perturbed quantities. The meaning of perturbed quantities are once we have introduced some students, how the velocity along x direction, perturbed velocity along x direction is changing, how the perturbed theta, that is theta is reference to the steady state theta, the perturbed theta is changing, how q is changing. It is something like, we go back to the spring mass system, when we did spring mass system, this is the reference, from here we are measuring x, which x was perturbed quantity, once we have given some students f. This x analogous to u theta q in 3 dimensions, right? Because it has only 1 degree of freedom, it has got 6 degrees of freedom. So you will get all those variables as the perturbed quantities. We are talking about only one equation, that is along x direction, so we have u, theta and q as perturbed quantities. And we need to track this u, theta and q and see how they are changing. If they come to 0, that means the system has come back to the equilibrium. So it's dynamically stable. Okay? That is the understanding. And that is the motivation behind solving this equation. We are behind solving this perturbed equation. So for the first time, we now have one set of perturbed equation, of course, along x-axis. And you know very well, we are operating in body fixed axis system. It's x-axis, the body fixed x-axis. Right? Let us have a closer look to this. When you note this equation, we use this is x, body fixed x, body fixed y, body fixed z. What is the meaning of W1? W1 is the component of velocity along z direction. This is W1 at steady state. That is very important. Okay. Let's say the airplane is flying at 2 degrees early. You know that what is the W1 component. For example, suppose this is the total velocity v and that all restricting to vertical plane. Then what will become W1? If this is alpha, W1 will be a component of v along W1 direction or z direction. Okay. It has two components, one v sine alpha, that component will be W1. If alpha is 0, W1 is 0. Right. So you can see that as the axis moves, the W1 component goes on changing. There is a smarter way of handling this. For simple reason, you know that the lift and drag, they will be always perpendicular to lift will be perpendicular to the velocity and drag will be opposing it. So if I choose an axis system such that the x-axis is pointed into the velocity vector in the vertical plane, then W1 automatically becomes 0, and it's very easy aerodynamics as far as mathematical manipulation is concerned. The lift will be perpendicular to the velocity vector along the local x-axis at steady state. So your W1 will always become 0 at steady state. So what is the meaning of that? We say define a new orientation for body fixed x-axis. So far, what was the assumption? The x-axis was aligned with some symmetric line, maybe Fujita's symmetry line or chord line. We are not very particular. Now we are putting a constraint. We are saying let x-axis points towards or points along v direction. V means total area relative velocity. And we are restricting our discussion in vertical plane. And such axis system is also known as stability axis system. So really what does it mean? It means this is the airplane, this is your x, this is the y, body fixed, this is the z. So at steady state, what I am saying, if the velocity vector is coming like this, I am actually pointing my x at steady state like xs, and this becomes my zs. This axis and zs are the stability axis system. What is the advantage of that? The moment I am using stability axis, xs and zs, you immediately see that the W1 will become 0 because the velocity vector is along this direction. It cannot have any component perpendicular to xs. So in stability axis system, W1 equal to 0 in stability axis system. What are two advantages we get as far as aerodynamics, computation or manipulations are concerned? we know lift will be perpendicular to this axis and drag will be like this. Similarly, another advantage you get that W1 becomes 0. So your this equation now in stability axis system, this in stability axis system, this will become M U dot, and this man will become 0, equal to minus mg theta cos theta 1 plus fax plus fdx. Further simplify. Please note that this is our stability axis system. You could very well understand the moment I am talking about x's and z's, the moment of inertia about x's and z's would not be same as moment of inertia about x and y and z. The small transformation you have to do, you will be very, very accurate. If the angle is very small, computationally it will not make much of a difference, but normal low speed performance. So now you could see that this is the perturbed equation of motion, and what are the things we know? We know theta 1. The theta 1 is the value of pitch angle at steady state. If it is 0, if theta 1 is 0, then it gets further simplified to mu dot equal to minus mg theta plus fx plus fdx. Now, we need to know what is fx, we need to know what is fdx. This is the perturbed aerodynamic force, the perturbed propulsive force. I need to know how do they change with u, how do they change with alpha, how do they change with alpha dot, how do they change with q, and so many other motion variables. That will come later. As on now, we have simplified the general equation of motion, and we have developed first equation in stability axis system. First equation mu dot minus mg theta cos theta 1 plus fx plus fdx, which is nothing but perturbed equation of motion along x direction. Our aim was to get perturbed equation of motion. We have successfully developed this, and we have tried to understand the small understanding so that once you use this equation, we are very handy. So we have demonstrated how to develop perturbed equation of motion. We have taken an example of u dot. I will quickly go through the other 2-3 equations. Since you have understood the first one, I am sure you will be able to follow it. I will just give you some indications that you will find any discomfort. So what we will do, let's see how much you have understood. What I should do for V? For V I should write V1 plus small v dot. For U I write U1 plus small u. For R I write R1 plus small r. For W I write W1 plus small w. For P I write P1 plus small p. And this is equal to mg sine phi 1 plus phi. What is phi 1? Phi 1 is the value of Planck angle at steady state. Cos of theta 1 plus theta plus f ay 1 plus fay plus f ey 1 plus fdy. Let us try to see what are these terms, especially fay1, the aerodynamic force acting at y, along y direction. You can understand, if the airplane is moving like this, cruising just like this, and if there is no side wind or side component of velocity, there should not be any force along that direction normally. But with the perturbation and the type of way the machine is flying, you can have forces depending upon what sort of perturbations are working on it. For example, if because of deflection the airplane started doing like this. Then it will have some force in y direction as well. There is a vertical tail. As the airplane moves like this vertical tail pushes here to our left, and I get a force along the y direction. So all those minus things we will see, those will be incorporated in FAY, perturbation. As far as steady state is concerned, we have explicit understanding of what is the aerodynamic force acting along y direction. If there is something or not, that's that we see depending upon situation. There could be a component of thrust along y direction. That is what F is y1. In reality, this is negligible, but you never know depending upon what is the orientation of the engine. Ideal designer will not like to have this. Sometimes, for different airplane, you may find some values, so don't get disturbed about it. Also, we need to use the earlier, as we use the first equation at steady state, I need to know that this W1, C1, phi1, theta1, 1, 1. This is automatically valid. Right? This is a steady state condition. So I expand this, take out this, and then expand sin phi1 plus phi cos theta1 plus theta, and use this small angle perturbation. So sin theta is equal to theta and cos theta is 1, and product of two perturbed quantities can be neglected. When I do that, then I get an equation of this form. M V dot, please understand the perturbed quantity, V dot plus U1 R minus W1 P equal to mg phi cos theta 1 plus f a y plus f p y. These are perturbed quantities. This is second equation you get. Okay. What is the value of W1? We have not stated that we are using a stability axis system up to this point for this equation. The moment we say we will be consistent and we will be using stability axis system, that means we have seen W1 is 0. So this equation further gets simplified to M V dot plus U1R equal to mg phi cos theta 1 plus fay plus fty. This is second equation, which is along y-axis, but we will say yes, stability axis. Right? Clear? What is phi here? Phi is the perturbed band angle. Phi 1 was 0, but because of momentarity disturbance, it may start banking like this. So that is phi. That changed from the steady state. The perturbed one. This is your second equation. So I now write this equation here, collect them at one place. So I write M V dot plus V1R equal to mg phi cos theta 1 plus fay plus fty. Similarly, we take the third equation. We are now trying to handle the third equation. We are trying to develop perturbed equation of motion. Please understand this is general equation of motion, right? So again, we will follow the same trick. M W1 plus W dot minus U1 plus small u Q1 plus small q plus V1 plus small v P1 plus small q equal to mg cos phi 1 plus phi cos theta theta 1 plus theta plus f az1 plus faz plus f pz1 plus ftz. Let us understand what is this ftz here. ftz means it is from the propulsion. I am talking about the thrust. Many times you will find the engine setting may not be exactly parallel to the reference axis. There will be some angle, towards left. That's why there will be a component of thrust coming from the engine itself at steady state. That is ftz1. And when we talk about perturbed ftz, it means as there is angle of attack change, as there is theta change, as there is a change in u, how this thrust is also changing along the local x direction. That x could be stability axis depending upon how you are developing the equation. Here, finally, you must be seeing we are converting every equation into a stability axis system. Right. Again, you follow the same technique, and then you do that. You first ensure that at steady state, this is true. Identical satisfied. So take out this foundation, apply small perturbation concept that product of two perturbed quantities is eligible, and then also phi and theta they are small, so apply the sine and cos approximation. Finally, you will get equation of this form: m w dot minus u1 q equal to minus mg theta sine theta 1 plus f sz plus f tz. This becomes my third equation. So I write m w dot w is perturbed w minus u1 q is equal to minus mg theta sine theta 1 plus f az plus f tz. So these are three force equations. We have three force perturbed equation of motion. Similarly, we develop perturbed equation of motion which denotes the angular motion. And we will do that next class. I would strongly recommend that please derive this equation yourself and ask yourself the question, what are these variables? Why we are doing all these things? Right? That is extremely important before we go on extracting information out of this. Thank you very much.